Hi everyone, welcome to my session. Hybrid Cloud GPUs, Democratize Secure AI with Confidential Containers. My name is Zvonko Kaiser. I'm with the Cloud Native team at NVIDIA, and I'm also responsible for all things related to Kata and confidential containers. This talk is part of a multi-series of talks that I gave in the past. So let's do some recap. One of the talks when I started to talk about confidential containers is to make the point that containers are not for isolation, right? Containers are more of a packaging mechanism to package a user space. It's not a means of isolation. So we need some sandboxing for containers to make them more trustworthiness, right? There are the different threat models. If you're an infrastructure owner, and so you want to protect your infrastructure from the workload, you use Kata to isolate your workload. But when we are talking about confidential compute, the threat model is 180 degrees, right? Where the workload does not trust the infrastructure. So that's why we're running then containers in a confidential VM, where a confidential VM is encrypting the memory, encrypting the state registers and all the other stuff so that the infrastructure cannot have access to it. Right? So we talked about how to protect the workload and isolating containers. But then we thought, okay, what about the thing that realizes or creates our confidential container, right? Where we extended the trust model also to the node where we're saying, okay, we need to protect also the node which realizes the confidential container because hypervisor is running on the node, QEMU is running on the node, all the helper libraries are running on the node that are realizing your confidential container, where I talked about, we need to have a full stack attestation, and attestation is the method of making sure that your state that you're expecting is really on the node, right? Comparing values that you measure during runtime with some reference values that you have offsite, which is called remote attestation, right? The point was, we need to protect the complete node from silicon up to the container with SBOMs, signed images, signed SBOMs, and all the other stuff that would entail the complete stack. So we went from container, we went to the complete node. And as we all know today, why we are here, Kubernetes is the platform of choice for any AI ML pipeline. So we need to think about how we are also protecting our Kubernetes cluster. AI/ML on public data is easy. Everybody with a credit card and enough money buys some GPUs, scrapes YouTube, scrapes TikTok, whatever else, creates Sora, right? But the really hard use case is to do it on private data, right? A recent Google study shows that 66% of enterprise companies have more than 50% of their private data sitting there without any means or any proper protection on how to process this private data. And there's even, not saying concurrency, but even in companies, you have teams that do not trust each other. So you need to protect the complete stack also from teams inside of a company, not between companies. Right. So what's the next step? I talked protecting the container, protecting the full node. The next step is really protecting the Kubernetes cluster. But what's the problem with the current Kubernetes state? If you look at it, Kubernetes is essentially a huge shared state between all pods. They're sharing the very same kernel. They're sharing the network stack. They're sharing storage, and they're sharing all the control plane. Once an attacker is on the node, it's completely game over for any Kubernetes cluster, because then you label yourself as a master, take over the master nodes, lateral movement to maybe other clusters or availability zones. And there's the other problem that tools like eBPF or any other observability tools on the very same node have the circular dependency problem, because you're trying to protect the system that you're currently running on. So if your kernel is compromised, eBPF will not help you because your kernel is already compromised, right? So there's this circular dependency that you have, which does not prove anything about your current state. So you always need something out of band. So what can you do, right? The point number one is we need something out of band. Because any complex system that relies on trusting itself and observing itself will not give you the trust that you need. Then we need to minimize the shared state for any component that's running on a Kubernetes cluster. And as well, beyond the shared state and out of band measurements, we also need identities. We need to know who is joining our cluster, who is this node, who is this workload, who is the network that I'm joining, who is providing the storage, and etc. So all those three operating principles can be applied to your compute, to the networking, to storage, and the control plane. Right? So we established the principles, now let's go from one overlay to the other. Compute overlay is kind of easy because we already established this with confidential container, right? We are creating a compute overlay in your cluster where your infrastructure does not have any access to it. We have a reduced attack surface, and the container runs in a trusted execution environment, be it SMP, TDX, or CCA. So all your data in use is protected. So this is kind of the overlay that you have, the compute overlay, and remote attestation is the out of band. And the shared state is minimized to only the trusted execution environment where your workload is running, right? So compute is done. So we have a compute overlay. Next step, we need a networking overlay, right? Because if you have a pod, the pod can talk to any pod in your cluster. But taking, for example, a rack pipeline, where you have embeddings, where you have inferencing, and you have re-ranking, you want to make sure that those components are talking in a compute overlay, identity-based, right? You don't want that any pod is joining your networking overlay that you have created for your rack pipeline. Only specific identities are allowed to join this overlay, and so that the rack pipeline is completely isolated from the Kubernetes networking that you have. In confidential containers, compute, we don't want to have any sidecar containers. We don't want to have any code injection changing. This is a static state that we want to keep, and we don't want to sidecar containers. And we don't want to have a global mesh because I want to protect my confidential data that I'm infusing in my rack pipeline, right? The meshes, the other meshes, the global mesh can be used for manageability of those containers, but not for our workload. And the identity of each of those components determines the reachability, right? What's the pipeline? And then with the out-of-band attestation, we can make sure that the container or the workload that is remotely attested can join a specific network overlay, which we can describe. The identity can be described by several factors that we have, like what's running inside my pod, which container I'm using. So you have several attributes that determines what's the identity and joining my networking overlay. And as well, we need confidential storage, right? You cannot use just any PV or CSI that you have on the node. It needs to be encrypted, but not only encrypted, it needs also to be integrity protected, and you need to have some freshness to be protected against replay attacks. There's a recent paper on TE fails on deterministic encryption, which means the same plain text creates the very same encryption text and ciphertext, and there is an attack vector on that malicious actors can use to deduce some information about your encryption. So there's always needs to be some randomness by padding or in creating some nonces inside of your encryption scheme. Right there are already encryption schemes like AES, GCM, or CHA-20 that have some kind of those nonces. So each plain text that's encrypted every time the ciphertext changes. So we need replay resistance with confidential storage. And again, this needs also to be completely isolated for each of those tenants. Right, we have an overlay for compute, we have an overlay for network, we have an overlay for storage, but we also need a control plane overlay because the control plane is shared between all the pods. And one model that we are thinking of is per tenant has one control plane. You eliminate the complete shared state, and additionally, you can run the control plane as well in a VM to isolate it even further between those control planes, right? Taking a step further, if you're already running it in a VM, why not run it then in a confidential container? Then, because you have all the remote attestation, all the principles and remote attestation capabilities that you have from confidential container, you would have it for your control plane. So you can be sure that you're running the things that you're expecting. Well, one problem with virtualization is nested virtualization. We don't want to have any nested virtualization. For example, if you're running on a CSP, you already get a VM. So how do you protect how do you want to run the control plane then in a VM as well? There are a lot of problems with nested virtualization, be it performance, be it security. So we want to eliminate nested virtualization to reduce latency and ambiguity. And then as well, the attestation of those systems can be really, really hard. So what we can do is, if maybe some older guys here remember still Zen with the DOM 0 and secondary VM problem, the use case where you have the service VM, which controls the user VMs, so that all the VMs are running on level L1 and not any nested virtualization with L2. And then we can provide a universal launch layer to adapt, let's say, for CSP, which is the Kata peer-pods model, right, where you can run a Kata pod on a CSP without utilizing nested virtualization. So this unified launch interface can be also extended to bare metal, let's say, for example, for an OpenStack driver. So you have the secondary VM as well on bare metal as well as on CSPs. We can take this even a step further. Why do we need even a host OS? Let's run those VMs directly on a type 1 hypervisor. If a VM breakout happens, let's create a void where an attacker does not have any possibilities. Well, there are still possibilities on a type 1 hypervisor, but we are reducing the attack surface dramatically if we are already running it on a type 1 hypervisor, right? So drop the host OS. Why do we even need it? And this smaller underlay enables for stronger insurances for us. And then we can combine all the attestations that we have already for the confidential VMs and the confidential containers, measure every stage of our platform, the type 1 hypervisor, the service VMs, the user VMs, and bind key releases only to successful remote attestation of those components. And then as well, as I talked before, we have also the freshness and anti-rollback capabilities in our network and on our storage overlay, so that we are combining all the platforms, SVMs, UVMs, into one big policy where we are saying, okay, only if my cluster adheres to my specific platform policy with those components, we are only to release a key into our CVM, and then you can decrypt your storage, or you're getting certificates for your networking, which could be the identity to join a specific network overlay. Right, as I already mentioned before, we can easily map down Kubernetes to the secondary VM, where we are running the control plane inside of a UVM, a user VM, completely isolated from other control planes that are used for other tenants. And then we can attest all of those components. And with the universal launch interface, we can run it on a CSP or on bare metal, on OpenStack, or any other private cloud on-prem deployment that it would have. So we have one single launch interface for a lift and shift of those confidential containers on any infrastructure as a service that you're working on. One thing we can also do is deploy the stack for density. So depending on your threat model, you could think of deploying those control planes for multi-tenants on one host, also the worker nodes on one node, and then as well the workloads in the pod that are running as well on another pod. If you want really, really strict isolation, you could think of a model where you're running one control plane per node, then you have the other worker per other node, and then the workload as well on one specific host. right? So you have complete isolation between all those components. If you want density, deploy the control planes on multiple control planes on one node or one host. So depending really on the threat model, either decide density or more isolation that you want to do. For networking and storage, the same, where we want to prefer SRIOV, isolated network devices or even PF pass-through devices inside of your network to have more control, so that the host does not have any access to those devices, as well as GPUs, right? You're doing the PF pass-through or VF pass-through to make it more isolated on the host. Storage as well, encrypted, integrity protected inside the guest, and only deliver the key on successful attestation and decrypt the storage inside of your VM. And for confidential containers, we are not using any shared FS between the host and the VM. It's all encapsulated inside of the VM. And we are ensuring only identity validated traffic and encrypted data flows with the confidential containers. Right, as I just mentioned before, everything is measured, everything is in a state that we're expecting, and only if those measured reference values compared to our reference values are valid, we are releasing keys, we are releasing the certificates, we are releasing the storage. Nothing is unmeasured. From silicon up to the container, we are measuring everything to make sure that the state is really that what we are expecting. Right, this enables us for hybrid cloud, independent of the infrastructure, independent of your infrastructure as a service. We have the same deployment patterns, we have the same attestation, different postcode, but still the same attestation, the same workload, independent of the infrastructure, following the same rules, independent what the infrastructure is provided. And we need a portable trust between any, because it should be a lift and shift strategy independent of the infrastructure. Right, as I said before, what we want to achieve is to run anywhere, be it on-prem, private cloud, CSPs, no application rewrites, no code changes, attestation gated identities and keys, and we isolate by design, depending on really on the threat model that you have. And we are also operating consistently with one launch interface, one policy model, and auditable evidence. And confidential containers makes hybrid cloud GPUI both portable and verifiable. Almost done with the talk. Future items, of course, are supply chain security. We also have side channel attacks that we need to think about. And physical attacks are usually excluded from confidential computing. But we are also looking into how we could protect to some extent against physical attacks. Last but not least, Google made an announcement today on the open collaboration for secure AI workloads. So the Kata container is currently integrated into the agent sandbox. Check the blog post with this QR code. So Kata containers is currently supported with secure agent sandboxing. Which leads me to my last slide. Any questions? Can you go to the mic?
Yeah, a couple questions here. First, what's the performance, the average performance hit from all of this overhead?
Virtualization overhead?
And cryptographic attestation overhead?
Well, attestation is not really an overhead, it's just the latency, before something starts up. So this would be part of your ramp-up phase. Integrity is a high demand on the CPU, and depending on how you implement it. So integrity, encryption is not, because most of the modern CPUs have encryption accelerators, but checking integrity is the really, really hard part. Virtualization of workloads is negligible because nested virtualization, we want to exclude nested virtualization. This is a big hit on performance. But usually only 1 in 1 million opcodes from the CPU are really trapped. So virtualization is really, really performant nowadays, if you're just talking about CPU virtualization. And if you have a GPU in a VM, depending on really how your communication patterns are, right? You have the term of arithmetic density. If you're doing more compute and you're compute bound, then there is no overhead, right? Because you're calculating all on the GPU. But if you have I/O overhead between the CPU and the GPU or networking, that's a different story, right? But it's not dependent on virtualization. It's more how the patterns you're exercising.
So is there like a percentage hit on average that you could expect, like 3 to 5%, 10 to 15%?
Okay, I've been doing performance engineering for a long time, and it depends. It really depends. So that's the only answer that I can give you.
Okay, awesome. Thank you.
Hi, thanks
Hi.
for the talk. How would you recommend that we generate these expected values when we most of the time don't know all of the inputs, especially for like public cloud? We don't know what they're running on the stack, and it's sometimes part of their IP, so they're not really open to giving us these information. So you said we can measure from silicon to application, but like, yeah, especially in that context, it's kind of hard.
Right, and the other thing is the CSPs are attesting themselves. So you have, again, the circular dependency because in the system that you're running, you cannot attest yourself, right? Yeah. So that's a CSP problem that I cannot answer, right? But I've seen many companies are now concentrating on enterprise and on-prem, where you have everything, at hand, and I can
Yeah, you mentioned the hybrid cloud use case, right? And the different shifts. So like, if I now use VMs from a cloud provider and put them into this highly trusted environment, I'm kind of like opening up my system to the cloud provider and be an untrusted party and then come in and like weaken the security of the whole system. Right, and then you don't have also the assurance bots running, for example, in the firmware, right? So exactly. Yeah. And the other thing, which is kind of part of the supply chain is attestation without reproducible builds, you can forget it, right? If you cannot recreate what the CSP is building, like the firmware or the underlying hypervisor, whatever else, no attestation will help you because they are providing the reference values, they are doing the attestation. I mean, it's a trade-off. If you trust your CSP, then yeah, you can offload it. I do not. Right? So that's why I'm saying most of the, if you really want to do confidential compute and you have like 50% of your data sitting at home, then you do on-prem. All right, thanks.
Hi, thanks for the talk, first of all. And I'd like to understand, I mean, if you consider a scenario where we have multiple tenants using confidential containers, each tenant has their own confidential control plane and everything, and they are running on the same set of nodes, like one node sharing multiple tenants, is there any limitation on the sharing of resources for a GPU, for example? Should we do anything different that we do in a standard shared environment? Like with SRUV and anything like that?
Well, depends on the isolation mechanism implemented on the GPU. Currently, it's only PF pass-through, right? One tenant gets a complete PF.
Mm-hmm. So like one single pod gets the entire GPU, and then if another pod needs it, it has to recover from the first one.
Exactly, and the VFIO substack will anyway do a reset, right? An FLR on the GPU, and then all the register state and all the state that you have from the different tenant would be wiped out. Mm-hmm. Right, so, and that's with the Hopper GPUs. Mm-hmm. So an FLR on the GPU and the VFIO stack will automatically make sure that when you hand over the GPU, it's in a proper state for the other one.
And do we have any expectation on to get SRUV VFs in this scenario?
Say again?
Do we have any expectation on how to work with SRUV VFs, like having separate VFs for each tenant on the GPUs?
Well, I cannot comment on that because the only supported method is PF.
Okay, thank you.
So after you get your collection of attestations, how do you use that to get a client identity? Do you register and get an OAuth identity? Like, what is your AI? How does your AI associate those attestations with, and then do things that allow them through policies?
Yeah, this really depends on. This really depends on what you as a
workload owner, you are satisfied as an identity. Depending on the use case, you may have other identities, and identity could be compromised of specific attestation claims, right? If you're saying, okay, this SBOM signature, this workload signature, this container signature, this user which is running in the container, et cetera, compromises my identity that I want to see. So it's like the primary key in your database, right? So you know which columns you need to pick to create a primary key to identify a specific record. That's the same for you as a workload owner, which is the relying party releasing the keys. You need to come up with the identity that you would need, right? For example, in the use case of federated learning, where you don't want that nodes are arbitrarily joining your cluster, you can define some kind of identity where you're saying, okay, only identities with this specific certificate can join my cluster. So a certificate could be a identity. Or you're saying the certificate, the state of your CVM, the state of the node, the state of the cluster, the state whatever. So you're combining or you're creating the identity that you want to see as a workload owner and who can join or not join your cluster.
Thank you.
Hi.
Hi.
At the start of the presentation, you had a slide on like a few of the don'ts, and one of them was with regards to like a global mesh. And I was curious if you could elaborate on that specific don't and why you're making that suggestion.
On the networking overlay, you mean?
Yeah.
For example, if you have confidential data, financial confidential data, do you want to share it with all the pods that are running in your Kubernetes cluster, or do you want to make it sure that the data that's going over your wire is only received and processed by the components that you are attested? So that's the point that I'm making, right?
So,
you can still use your global mesh. I'm not saying don't use it ever, but as a confidential compute overlay, you should protect the networking overlay that's compromising your specific workload. Like I said, RAG, right, where you're inputting like any PDFs. You don't want that your load balancer reads all the data or whatever else until it reaches your workload.
Right, so like a service level isolation rather than...
Yeah.
Okay, all right, that makes sense.
Yeah, but still use a global mesh for other manageability tasks, right? You could still use it for sizing or, oh my goodness, for any manageability task of your workload.
Yeah, that makes sense.
Yeah.
Okay, thank you.
Hi, so I probably missed you said for the future, you have one thing like a physical attacks. Do you have some ideas? You have access to operating system level. I can take the hard drive, everything.
Yeah, interposers, you can do anything, you can read out. So there's, yeah, we have 2 minutes. There are techniques how you could, for example, timing. If you know, right? If you know how much your function takes, right? And you could do some measurements of your function runtimes and then make it independent of the clock or independent of how fast the CPU runs. So you have a measurement of some runtimes. And so if there is an attack in between of those functions, depending on your statistics, you could see that something is going on and just shut down the VM, right?
I thought you
there is one thing.
GPS.
Well, you could do something like that as well. We have one more. We have just 1 minute. Thank you.
Having talked about SRIOV and function-based kind of protections, I'm wondering how much of this work has to go into the PCI aspect of things and things like PCI errors.
Okay, that's a great question. So current generation of GPUs with CC are working with bounce buffers. So they have a small region of memory where they're doing like a Diffie-Hellman and doing AES GCM encryption of the traffic between the CPU and GPU. But PCI Express 6 has TDISP and integrity and encryption decryption capabilities. So it all happens on the PCI Express bus. GPUs or other accelerators are only admitted into the CVM after the PCI Express bus says, okay, I'm fine with that. And there's a specific state machine of things that need to go with the device to happen that it's admitted into the GPU. So all the attestation happens on the PCI Express bus. And then endpoint to endpoint communication are encrypted and integrity protected on the PCI Express bus.
That's awesome. Thank you.
Okay, thank you all for attending. Catch me on the hall in the expo hall. I'm around. Thank you.